we have one more section before we start covering the properties of acids and bases. And this is going to mix together our equation we just learned with molarity with some of the concepts from first semester and stoichiometry. This is called volumetric analysis. So in the real world, in labs, we don't really typically have things react perfectly stoichiometrically, right? We don't have this like perfect ratio of this thing reacting exactly with the correct amount of this other thing. Usually we have what's called a limiting reactant, which is the reactant that's going to limit the scope of the reaction, and an excess reactant, which kind of exists in obviously excess, meaning that we have extra of it at the end. And so with volumetric analysis, we're going to use that to determine the limiting reactants, like which one is the limiting reactant of all the reactants based on quantity. And then we're going to use that to determine how much of the product could actually form. And we're going to tie this in with molarity. We will use this very frequently with acids and bases, particularly with neutralization reactions, titrations, and trying to figure out the pH of a solution at a given point. So a limiting reactant then, by definition, it says that in a given chemical reaction, the limiting reactant is the reactant which determines the maximum amount of product that can be produced. Okay, so one of the reactants, if there's more than one, is going to dictate how much product we can make. Okay, and so the question, right, if we're trying to put this, in simple terms and not chemistry and stoichiometry terms, so let's say it's something like this. A brownie mix requires 2 eggs, a half a cup of oil, and a quarter cup of water. You have 5 brownie mixes, 12 eggs, 4 cups of oil, and 3 cups of water. How many brownie mixes can you make? Which ingredient limits this? So right, it's going to be questions like this, right, except just involving balanced equations and stoichiometry and molarity this time. Okay, so I'm going to give you a few seconds here to try to do this on your own and get an answer, and then I'm going to show you how you would do this. So let's see if you can figure it on your own, and check in here in a few seconds. Okay, so I have pulled all of the ingredients we had up here together to form as many different brownies that we could possibly make, right? So we had 5 boxes of brownie mix, we had 12 eggs, we had 4 cups of oil, and we had 3 cups of water, right? So how many can we make with all of that? Well, I pulled my 5 brownie mixes. I gave them each 2 eggs and 1 half cup of oil and 1/4 cup of water from all my ingredients here. So I could make a maximum of, it looks like, 5 trays of brownies, okay? I have leftover eggs, I have leftover oil, and I have leftover water. The one thing I don't have anything left over of is the brownie mix, meaning that in this particular reaction, okay, my limiting reactant are the brownie mixes, okay? If I had another brownie mix, if I had a 6th one, I could make a 6th one, right? I could grab 2 more eggs, a half a cup of oil, and a 1/4 cup of water, and I could make a 6th one, but I don't have that, right? And so the brownie mix is the limiting reactant here. And then we could say that the excess reactants are everything else. I have excess water, I have excess oil, right, and I have excess eggs, right? I've got all of that left over here. The one thing that determined, right, how many I could make total was my boxes of brownie mix, right? I only had 5 of them. So we're going to do something similar here with chemicals and stoichiometry in just a moment to see how much of a product we can actually make. Okay, so let's apply this to a chemical equation. So they're going to look kind of similar to some of the stoichiometry problems from first semester, but the questions are going to now involve molarity and talking about limiting reactants, so let's try to navigate this. So we're going to get an unbalanced reaction to start. We're going to start by obviously balancing it. And now instead of saying 5 grams of this reacts, how much product can you make in grams? It's going to say if 10 milliliters of 0.500 molar CuCl2 reacts with 10.0 milliliters of 0.35 molar Na2S, what is the limiting reactant, right? So these are my 2 reactants. Think of this as the brownie mix, the oil, the eggs, and the water. This time there's only 2, right? And I'm saying how much I have of it really in moles here, since I have a volume and a molarity, right? And so how they react, the proportion in which they react is based on the balanced equation, right, and our coefficients here. So we're going to have to balance it. And that's going to tell us just how much of a product we can make, right? And so we're trying to figure out which one is limiting my products here. Is it the CuCl2 or is it the Na2S? So we're going to check that. C says, what is the mass of Cus produced from this reaction? And so when we're solving B, we're actually going to basically solve C at the same time, as how much copper 2 sulfide am I making when I do this, right? Because this is going to dictate how much we can make. Like before, we could only make 5 brownie mixes. How much Cus can we make, okay, in grams? And D says, what is the concentration of sodium chloride when the reaction is complete? Okay, so we're going to figure out what's the concentration of this, right? Since it's aqueous, it'll be dissolved in water. But in order to do that, we got to figure out which one of these two is the limiting reactant, because that dictates how much product we can make. Okay, I went ahead and balanced this one because it's pretty easy. It just needs a 2 in front of the NaCl here. So if you need help with that, see me, but I think you guys are able to do that on your own. Okay, so how do we actually solve this, right? How do we figure out which one of these is the limiting reactant? Basically, what we're going to do is set up some stoichiometry, okay, where we're trying to figure out, and we could pick either the CuS or the NaCl. We're trying to figure out how much of a particular product we can make. I'm going to pick the CuS because C is asking about, part C is asking about how much CuS can we make. So I'm going to pick CuS as our product we're looking for. But instead of starting with grams, right, and molar mass, this time we're starting with volumes and molarity. So we're going to set up 2 stoichiometry problems here, or 2 stoichiometry setups, where we're going to start with these amounts, which turns things into moles. Okay, so step 1 is going to be convert to moles, right? Okay, because we have to have things in moles in order to use a mole ratio, which was always the second step in a 3-step problem. From first semester, right? It was a mole ratio, moles of what you're looking for over moles of what you were given from the balanced equation. And then 3, okay, is convert to grams, okay, if necessary, right? So we're going to need to do that here. All right, convert to grams if necessary. So we're going to set this up. We need to get these values here of CuCl2 and Na2S into moles. So in order to do that, right, my equation is molarity is moles over volume. So if I want moles by itself, right, that's going to be molarity times volume, and volume must be in liters, right? So my first stoichiometry setup, let's pick the CuCl2, okay? And so to get that into moles, we're going to take the molarity, which is 0.500 molar. We're going to multiply that times the volume in liters, so we're just going to divide that 10.0 milliliters by 1,000, or just move the decimal 3 places to the left, right? And that would get me, technically, if I want to be specific here, that would get me moles of, right, CuCl2, okay? Okay, I went ahead and corrected that to get the CuCl2 in there. So I've got that converted to moles. Now I would do a mole ratio. And this is just going to look just like it did first semester. Moles of what we're looking for over moles of what we were given. We're going to look for CuS. We could pick either one. In fact, we're going to eventually have to do it for the NaCl as well, but we need to figure out which one of these is the limiting reactant first. We're looking for CuS. This time we started with CuCl2. That is a 1-to-1 ratio, so that's all going to stay the same. And the last thing to do here is to convert to grams if necessary. Well, part C asks what's the mass in CuS, so we are going to need to convert this to grams. So we need to multiply times the molar mass of CuS. Okay, so I'll just put that up, put this up here. Molar mass is 95.62. Okay, so when do we need that? So 95.62 grams of CuS for every 1 mole of CuS. Okay. And now we're going to just go ahead and do all that mass. We got 0.5 times 0.01 times 1 times 95.62. Okay, and then to 3 significant figures, that's got 3, that's got 3, that's got 4. To 3 significant figures, that's going to be 0.478 grams of CuS. Okay, so we did that for the first reactant here, meaning that, if this thing reacts all the way, the maximum we can make here is 0.478 grams of CuS. Let's do it again, but this time for the Na2S. It's going to look very similar in terms of setup. We're going to take our initial molarity, 0.350 molar, right from the problem, Na2S. and we're going to multiply times that volume in liters, which is also 0.0100 liters. We're going to set up our mole ratio. Moles of, we're looking for CUS as well. We started with moles of Na2S, still a 1-to-1 ratio, and then we got to multiply times the molar mass of CUS, which is 95.62. Okay, and all that multiplied together, 0.350 times 0.01 times 1 times 95.62. Okay, this is 0.335 grams of CUS. Okay, so what is that telling us here? Based on our starting amounts of CuCl2 and Na2S, if I was able to use all of the first one, I can make 0.478 grams, and if I was able to use all the second one, I can make 0.335 grams. The reality is here that we can't make more than the one that is the least amount. This is our maximum, right? Going back to the brownie example, right? We could only make 5 trays of brownies with all of our ingredients. So here, with all of our ingredients, I could only make 0.335 grams of CUS. Okay, so the limiting reactant for this problem is the Na2S. Okay, because it dictates this is the maximum amount of CUS I can make, which means that there is extra CuCl2, okay, at the end of this thing. The nice part for doing all that work in B is that C is very simple. What is the mass of CUS produced from this reaction? Well, we're going to go back and basically just look at what did we make, which one was the least amount, okay? And we made, I believe, it was 0.335 grams of CUS, right? That's the maximum amount of CUS we can make. We couldn't make the one that was like 0.478 something. Okay, this was our maximum, so that's what we end up with. Okay, so how do we answer D? I like D as a question. What is the concentration of NaCl when the reaction is complete? Right, so this was a 2 here. Let's not forget that. How am I going to figure out what the concentration of this is? Well, now that I know which one of these things is the limiting reactant, okay, which was the Na2S, that's going to dictate how much NaCl could be made in moles. And its concentration, right, is moles over volume. So I need to find moles of NaCl that got made, okay, and I need the total volume. I need those two things here. So it shouldn't take too long, actually, since we know the Na2S is the limiting reactant, right? And so our volume of the, molarity of the Na2S was 0.350 molar, Na2S, and our volume was 0.0100 liters, okay, and that would be moles of Na2S. I want moles of NaCl, right? So this is really just a one-step problem. NaCl is what we're looking for. That's a 2 this time, right, from our balanced equation. And so what we're going to have is, right, 0.35 times 0.01 times 2, and we get 0.007, and to give it the right sig fig, 00 moles of NaCl. Okay, so this was my moles of Na2S. This was my limiting reactant. That's why I picked this one and not the information about the CuCl2, right? Okay, just to make sure here we're clear on this. This comes from the limiting reactant. That's why I picked this one. It dictates how much I can make over here. Okay, so I have the top part of my molarity equation, right? I have the moles of NaCl. I need the total volume. Well, when I mix these two solutions together, right, there were 10.0 milliliters of this one and 10.0 milliliters of this one. So the final volume here is just these two things added together, right? But they got to be in liters because my molarity equation needs the volume in liters. So my total volume is just going to be 0.0100 liters plus 0.0100 liters, right? That's going to be 0.0200 liters. So I've got both parts of my molarity equation. I have my moles, which were 0.00700 moles, divided by 0.0200 liters. And we'll plug that into the calculator. We get 0.35, and we'll give it 3 significant figures, 0.350 molar, right, is the concentration of my NaCl. So there we go. Okay, so we're going to give this one to you to try, so you'll need to try this one in your notebook. All right, so first thing to do, right, is to balance the reaction. Part A, right, balance the reaction. B, if 15.0 milliliters of 0.200 molar AgNO3 react with 25 milliliters of 0.100 molar CaCl2, what is the limiting reactant? C, how much AgCl is produced in grams from the reaction in B. So it'd probably be a good idea to pick AgCl as your product when you are trying to set up your stoichiometry in B. And D, what is the concentration of CaNO3 after the reaction in B has occurred? So that's just like the one on the previous slide there. So try these, and we'll see how you do. Okay, so running through these real quickly. If we take our information from B, we set up two stoichiometry problems, right? Molarity times volume to give our initial moles, times the mole ratios here, and then times the molar mass of AgCl. Right, AgCl is the one I would pick since that's what C is asking about. With the first one, we would get 0.430 grams of AgCl, and with the second one, we would get 0.717 grams of AgCl. Which means that the first one is going to limit how much we can make, right? Our AgNO3 made the least amount, so that's all we can make, okay, from this setup here in B. So AgNO3 is the limiting reactant. 0.430 grams would be my answer in C, right? That's how much I could make as a maximum. D, we're going to take our limiting reactant now, the AgNO3, molarity times volume, to get moles of AgNO3, and then to figure out how many moles of CaNO3 use my mole ratio, 1/2 there, and I get 0.00150 moles of CaNO3 I need the volume, right, for a molarity equation. I need the moles, which I have, and then the volume. The volume needs to be in liters. I had 15 milliliters and 25 milliliters. 0.0150 liters plus 0.0250 liters is 0.0400 liters, so just adding my two volumes together here in liters. And to calculate the molarity of it, 0.00150 moles divided by 0.0400 liters is 0.0375 molar.